Now that we have reached this point, let's try to substitute the value of yb inside this equation, and let's get what was yb. Yb was this equation, so I can get this and then copy it and get here and paste it, and we have that yb equals n yv over negative zv. So yn equals 2 multiplied by n yv over negative zv of t minus b minus t plus b over t minus b. Similarly, we can see from the symmetry that xn will be equal to 2 multiplied by n multiplied by xv over negative zv, and here r minus l minus r plus l over r minus l. So the xn and yn are somewhat symmetric. Let's make sure here, and so it's correct. Okay. Now, what is the relation between yn and yc? We know that yn actually equals yc over wc, which is equal to yc over negative zv. So we can see that yc actually equals yn multiplied by negative zv. So from here, we wish to get yc in order to complete our matrix. So we can actually do something like this, negative zv over negative zv. We have not changed anything like this, but we now can say that yn equals 1 over negative zv, which is 1 over w, multiplied by here 2n yv over t minus b minus t plus b multiplied by negative zv over t minus b. So that's the new equation we have. We have yn equals something over negative zv, but this something is actually yc. So we can see here that yc finally equals 2n yv over t minus b minus t plus b over t minus b multiplied by negative zv. So we can say that this is positive zv. Like this, I think this is correct, except if I have made some sign wrong, I will check this now. And similarly, xc will be equal to 2nxv over r minus l plus r plus l over r minus l multiplied by zv. Okay, let's now put these values inside our matrix here. So we see that xc depends on xv and also zv and nothing else. So we can see here that this here has some value here and then 0, and some value here and then 0. The value in the first here will be 2n over r minus l. 2n over r minus l, and the value here that's multiplied by zv is actually r plus l over r minus l. R plus l over r minus l. Similarly, yv will be equal to 0 here, and here we have 2n over, instead of r minus l, we have t minus b, and here we have r plus l over r minus, no, not r plus l, we have t plus b over t minus b, and here we have 0. So we have made those two rows of this matrix. I can make them a little bit smaller in order to have space for the third row of this row. Now, how do we get the value of zc? Again, there is no physical value of zc because we actually, when we do projection, we eliminate this z component. But we need some z value in order to do some z testing, and we need it to be logical value of z. First of all, we know that zn equals zc over wc. But we also know that wc is actually negative zv. So zn equals zc over negative zv. So this is some relation that has to be met because we already chose the value of WC, and this value has to be global value. Now, what about ZC? We do not know what value does ZC have, but at least we know that ZC does not depend on X or Y, so we can put a 0 here and a 0 here because the value of Z, the value of the depth, does not depend on X or on Y. But it will probably have some dependence upon ZV, and it might have some free components. So we have two parameters here, A and B. And now we wish to get the value of A and B in order to get the actual value of ZC in order to complete our perspective projection matrix. Now, what information do we know about this ZC? So we can get here and say that Zn, let's get here, and we might say that Zn equals A multiplied by Zv plus B over negative Zv. Now, what do we know about Zn? We actually know that the points inside this frustum, the points between negative n and negative f, have to be mapped to be inside negative 1 and 1. But there is another OpenGL convention here that actually this negative n gets mapped to negative 1 and this far plane gets mapped to positive 1. Remember here that we had this drawing where the camera is facing in a negative z direction, so the f or the far plane has a more negative value than the near plane, so because this is the negative z direction. But actually, after we do this projection, OpenGL decides that the negative n will be mapped to negative 1 and the negative f will be mapped to 1, and so the far plane will have a more positive value of z. So this is somehow equivalent to changing our coordinate system from being x, y, and z here to be x, y, and z in the opposite direction. We are transforming from a right-handed system to a left-handed system, and this is required by the internals of OpenGL. So let's try to use this information here. We see that negative n mapped negative 1 and negative f will be mapped to 1. This means in our equation here that if ZV equals negative n, Zn will be negative 1. So let's substitute two substitutions here. Here we have that negative 1 equals a negative n, negative a n plus b over negative zv, which is over negative n, which is n. So this is some equation, and the other equation will say that 1 equals a negative f, so negative af plus b over negative zv, which is over f. So now we have that negative n equals negative an plus b, and we also have that f equals negative af plus b. Now let's organize them a little bit. We have n plus an, n minus an, n minus an plus b equal 0, and we also have that f plus af minus b equals 0. So let's add those equations together. We will have that n minus an plus f plus af equal 0. And so we wish to get the value of a. So a f minus n plus f plus n equals 0. And so actually a equals negative f plus n over f minus n. And that's a. So let's get b. b equals an minus n, which is actually equal to negative f plus n over f minus n. So this is a multiplied by n negative n, which is n f minus n over f minus n. So this is negative n. So this is actually negative fn, so it is negative 2fn, and negative n square plus n square will get deleted. So you'll have here f minus n, and by this we have created the b and we have created the a, and we can substitute in our projection matrix. And this is our final projection matrix finally. This projection matrix will map all our vertices in the view space into this clip space, and after mapping to the clip space, we will do the actual clipping, which is the comparison of all the points by WC and negative WC to see which points will get discarded and which point will remain, and after that we will divide by WC in order to get to the normalized device coordinates where we perform the depth testing, and after that we will have some screen coordinates, some actual pixel coordinates which will be drawn on our screen. A final note here is that usually this view frustum is somehow symmetric, and so L equals negative R and B equals negative T, and this will simplify our projection matrix to be something like this. So 2n over R minus L, note this is not a negative, this is the bracket, 2n over R minus R will give us n over R here in this point, and we have 0 here. This will be R minus R, which is 0, and this will be 0. Here we have 0, and here we have 2n over 2t, which is n over t, and then we have this 0 and 0. Here we have 0, 0, negative f plus n over f minus n, and here negative to f n over f minus n, and the final row will be the same, 0, 0, negative 1, and 0. So actually, this is the final matrix that you will find inside actual code libraries, and we will investigate this in the next video.